You've most likely already had a fair bit of experience solving rational equations, um, but let's look at this in a little more detail and talk about some of the things that can trip you up. So up till now in this chapter, we've just been simplifying things. We've been writing one expression in a different way. And keep in mind that we've been writing the restrictions because, strictly speaking, we're saying that the one expression is equal to another expression for all values of the variable. The problems we're looking at here are a little different. We're solving equations, which is fundamentally different. The instructions are different. Right off the bat, it says solve. And what that really means is that we're looking for all values of the variable that make the statement a true statement. And for an equation, that means there might only be one value or a couple, in the case of, let's say, a quadratic equation. And those values we call solutions. All right, so also keep in mind that now that we're dealing with an equation, we can do all of the tips and tools that we've used in the past for solving equations. We can add the same thing to both sides of an equation. We can multiply both sides of an equation by the same thing. So when you look at this equation, x over 5 equals 2 over x plus 3 over 5, one temptation is to start trying to simplify it the way we've simplified other rational expressions and create a common denominator. Well, that's not necessary, and in general it's going to be a little bit more work than we have to do. But the idea of a common denominator is quite important. We can take advantage of the technique of multiplying both sides of this equation by the same thing to get rid of the fractions, to end up with an equation that is not involving any rational expressions. So the key here is to identify the common denominator. In this case, the common denominator is 5x. So if we multiply both sides of this equation by 5x, then we will get an equation that doesn't involve any fractions whatsoever. Now, keep in mind, just take a look at the left-hand side. I'm not multiplying this by 5x over 5x. That would be something I would do if I wanted to create an equivalent expression. So I'm not creating an equivalent expression. All I'm doing is multiplying both sides of the equation by 5x. I'm creating something quite different on the left and something quite different on the right, but the equality still holds. Now, when you do this product, don't write. The whole point is to get rid of the fractions. So ask yourself what cancels out when you do the product. With 5x times x over 5, the 5's cancel, and you're left with x times x, which is x squared. On the right-hand side, keep in mind you're multiplying that 5x by both terms in the binomial. So when you multiply it by 2 over x, the x's cancel. You're left with 2 times 5, which is 10. And then when you multiply it by x plus 3 over 5, the 5's cancel, and you're left with x plus 3 times x. Now, if you expand this, you can see what kind of equation it is. It looks like a quadratic equation because of that x squared term. But notice that we have an x squared term on both sides. So if we subtract x squared from both sides, we get 0 on the left, and we just get 10 plus 3x on the right. And that's really a straightforward linear equation. We can solve that the way we've solved hundreds of other linear equations. Just subtract 10 from both sides and then divide both sides by 3. So this one value, minus 10 over 3, will make the original statement true. And it's worthwhile going back and plugging it in. Now, it's obviously a lot easier to plug in an integer. You could do that in your head. Something like minus 10 over 3 might take you a little longer, but it is worthwhile just going back and plugging it in to make sure that it does indeed make that statement a true statement. Now, one of the things we haven't talked about here that we spend a lot of time talking about when simplifying rational expressions is restrictions. Strictly speaking, we don't need restrictions here because we're not trying to say that some expression is equal to another for all values of x. We are making a very different claim. We're claiming that if x is equal to negative 10 over 3, then that expression on the left is equal to that expression on the right. And that's very, very different. However, I would still suggest that you pay attention to restrictions. In this case, there's only 1 because of that denominator x. We have x is not allowed to equal 0. Now, the reason I suggest you do this is because it can save you from making a statement that is just simply false. Occasionally, you will get a solution to an equation that turns out to be a restriction, which can't be true. So it's worthwhile just checking that your solutions are not the same as any restriction. If you have gone to the trouble of plugging in your solution to make sure that it actually generates a true statement, it's probably unnecessary to do the restriction, but it's usually a little quicker to come up with the restriction. So if you're in a hurry, that would be certainly the first thing I would do. All right, let's take a look at another example. Let's say we are asked to solve the following equation. 5 over x minus 2 is equal to 9 over 3x minus 6. Now, you've seen this sort of equation before, where it's a simple fraction on one side and a simple fraction on the other. And the technique that you've probably used in the past is cross-multiplying. So what do we get when we cross-multiply? We get 5 times 3x minus 6 is equal to 9 times x minus 2. If we expand, we get 15x minus 30 is equal to 9x minus 18. I'll collect the x's on the left by subtracting 9x from both sides, and I'll add 30 to both sides, and then divide both sides by 6. And I get x equal to 2. Big problem, though. If you go back and plug it in, you see that you get 5 over 0 is equal to 9 over 0. And you cannot claim that those are equal because neither of them is defined. And if we had just taken the trouble to write the restriction, x is not allowed to equal 2, we would not make the claim that 2 is a solution to this equation. So since we don't have anything else to choose from, we simply have no solution here. Now, you can see quite clearly why there's no solution if you just simplify the right-hand side. So the right-hand side actually has a common factor of 3. And when you eliminate that common factor of 3, you're left with 3 over x minus 2. So let's look at this expression, or this equation. We have 5 over x minus 2 is equal to 3 over x minus 2. So in other words, no matter what x is, the denominator is going to be the same. So you have 5 of a certain type of fraction equal to 3 of the same type of fraction. That's never going to happen. But when you let x equal 2, you get denominators of 0. And so you can end up essentially proving nonsense if you allow for division by 0. And you can check out my other video where I prove that 2 is equal to 1, which is something you can only do if you allow for division by 0. All right, let's a little comment too on the cross-multiplying. Cross-multiplying is really just a sort of specialized application of the same technique that we used in the first problem here, which is multiplying both sides by the lowest common denominator. It's actually better to try to identify the lowest common denominator. If you cross-multiply, sometimes you will generate equations that are a higher degree and more difficult to solve, if not actually impossible to solve. So you want to avoid just blindly cross-multiplying. It's much better to multiply both sides by the lowest common denominator. In some cases, that ends up being the exact same thing. So if you're in a hurry, you can try cross-multiplying and just hope that you've got the lowest common denominator. Let's take a look at a couple of more examples here. How about, I'll change back from red to blue, or black. How about if we're asked to solve x plus 18 over x plus 7 equal to 4. So there's only the one denominator, so it's pretty easy to identify the lowest common denominator. It's just x plus 7. So I'll multiply that by the left and the right side of the equation. I end up with x plus 7 times x. That's x squared plus 7x And then when I multiply x plus 7 times the fraction, 18 over x plus 7, the x plus 7's cancel, and I'm left with 18. On the right-hand side, I have 4x plus 28. So this truly is a quadratic equation. We can't get rid of the x squared, which means we solve it the way we solve all other quadratics, which is to get everything onto one side. So I'll subtract the 4x, and then I'll subtract the 28. And factor it if you can. That's usually the easiest way to solve it. This one does factor. It factors as x plus 5 and x minus 2. And therefore x is equal to negative 5 or 2. The restriction was negative 7, which is not one of our solutions. So you can be pretty confident that these are correct. Since they are both integers, it's easy enough to check. For instance, if you plug in 2, you would get 2 plus 18 over 9, which is 2 plus 2, and that's certainly equal to 4. And you can try the same with negative 5. Let's take a look at one more. So what if we're asked to solve 5 over x minus 1 minus 12 over x squared minus 1 equal to 1? Now, x minus 1 is not the same as x squared minus 1. So what do you do here? Do you multiply both sides by both of the factors, x minus 1 and x squared minus 1? No, that's going to create an equation involving x cubes, and you really want to stay away from that. Just as before, it's going to be a lot easier to identify the lowest common denominator if you factor all the denominators. And you should really factor everything, because you might find you can even simplify some of the expressions in the equation. In this case, obviously, you won't be able to simplify those expressions, but if I factor the two denominators, cat goes on the floor, if I factor the two denominators, I can see that they do actually have a common factor of x minus 1. So, in fact, the lowest common denominator is just x minus 1, x plus 1. And if I multiply both sides by x minus 1, x plus 1, I will get rid of all the fractions. So when you multiply both of those factors by 5 over x minus 1, the x minus 1's cancel, and you're just left with 5 times x plus 1. Then when you multiply both of those factors by the second fraction, both of them cancel, and you're just left with the minus 12. On the right-hand side, obviously you just have the x minus 1, x plus 1. So let's expand and collect terms and see what we get. 5x plus 5 minus 12 is equal to x squared minus 1. So again, this is a straightforward quadratic, and I'll get everything on the right-hand side and see if I can factor it. So I'll subtract the 5x from both sides. 5 minus 12 is negative 7. If I add 7 to both sides, I get plus 6. And sure enough, that does factor quite easily. X minus 2, x minus 3. So x is equal to either 2 or 3. The restrictions here are x cannot equal plus or minus 1. Neither of those is equal to one of my solutions. And again, pretty easy to check since the solutions are integers. If you plug in 2, for instance, you get 5 over 1 minus 12 over 3. That's 5 minus 4, which is definitely equal to 1.